So now we're going to use the initial conditions to figure out our values, our two constant values, A1 and A2, that is in our proposed solution for current for the LC circuit. So one thing we need to do, because this is a second order equation, we need to have two initial conditions for the variable that we're studying here. So we're studying I. Right now we have one initial condition for I. And because we have a second order equation, that means we need two ICs for I. So we have one initial condition right here. And what we'd like to know is what is di dt at time equals 0. So the other piece of information we have is this v naught at time equals 0. So let's use that. And we'll just plug that straight into the inductor equation. So the inductor equation at t equals 0, the voltage across the inductor is v naught, and that equals L times di dt. All right, and that means that di dt equals v naught over L. So now I have two initial conditions in terms of I. There's one, and there's one there. And we can use these now to go after A1 and A2. First off, let's plug in I for time equals 0, and then see if we can work out something over here. So that means at time equals 0, the current is 0, and that equals A1 cosine omega naught times t of 0 times 0 plus A2 times sine of omega naught times 0. And what does this evaluate to? Okay, so this is sine of 0, and sine of 0 is 0. And cosine of 0 is 1. So that comes up with 0 equals A1. Okay, and A1 equals 0 means that this entire term of our solution just dropped out. All right, let me write what we end up with. I equals A2 sine omega t, omega naught t. This whole term here just dropped out of the solution. So here's our proposed solution down here. Now we need to go after A2. Let's do that. As you might suspect, we're going to use our second initial condition to do that. So to use our initial condition, we need di dt. So let's take di dt of this. So we're going to take d dt of this whole equation. And on the left side, we'll get di dt. And on the other side, we'll get d dt of A2 sine omega naught t. Okay, so far so good. Let's roll it down again. So let's take that derivative. We get di dt equals A2 comes out of the derivative. And the derivative of sine omega naught t with respect to t is omega naught times cosine omega naught t. And we apply our initial condition. Let's go to t equals 0. And we know that di dt was v naught over L equals A2 omega naught cosine of omega naught times 0. And cosine of 0 goes to 1. And so we can solve for A2. A2 equals V naught over L, and omega naught goes down here. So now we've solved for our second adjustable parameter, and we can write I. I was A2 sine omega naught t. So let's fill it in for A2. I equals A2 is V naught over L omega naught times sine omega naught t. And I want to go back now. I want to write this a little bit different. I want to go back and plug in our value for omega naught. So if we remember, we said omega naught equals 1 over LC and the square root of that whole thing. So now L omega naught equals square root of 1 over LC times L, and that equals square root of L squared over LC, and that equals square root of L over C. Lastly, I'll write 1 over L omega naught equals square root of C over L, just the reciprocal. And now we can write I equals square root of C over L times V naught sine of omega naught t. And that is the solution for the natural response of an LC circuit. It's in the form of a sine wave, and the frequency is determined by omega naught, which is the two component values, and the amplitude is determined by the energy we started with, which is represented here by V naught, and the ratio of the two components again. So this is why I said at the beginning that this is where sine waves are born.